Welcome to the lecture on distinct zones in fusion welded specimen. So, basically we are talking about the weldments which are formed by the fusion welding process, and as we have seen that when the welding is being carried out. So, you have the maximum temperature in the weld pool, and then in the transverse direction the temperature goes on decreasing. So, you will have the different zones which are subjected to the different temperatures, and because of that you will have the different properties of the material. So, the welded joint varies in metallurgical structure from point to point with consequential variation in mechanical properties. So, basically when your the weld metal zone which has the maximum temperature, from there as you move towards the transverse direction. So, you will have different temperatures to which the material's temperature is raised, and for that the properties are also changed. So, there is change in the mechanical properties. Now, extent of this zone will be depending upon various factors like heat input per unit time, then you have the welding velocity, and you have the physical properties of the material like the thermal conductivity, or thermal diffusivity in true sense you can say. Then you have the melting point. So, all these things are also determining that what will be the width of or the dimension of that particular zone will be. So, basically when we talk about the weldment, then a weldment has basically three different zones, as we see that a weldment can be divided into three distinct zones. So, first zone is the weld metal zone, and then you have so that weld metal zone, basically that zone which will be forming the weld bead. So, that is your weld metal zone. Then the next zone will be the heat affected zone. So, this heat affected zone is that zone where the properties are affected, the structure is affected because of the heat which is flowing, and consequently the temperature is changing. So, there will be heat affected zone, and after that to its side you will have the unaffected zone, that is unaffected base metal zone, or we call it as the BM or BMZ or base metal zone. So, you will have three distinct zones in those cases, and you can have we can see by graphically that you have basically you have the fusion zone which will be here, and then you will have so in the fusion zone, and on this side you will have the grain structure. So, this way these are partially melted grains. So, and then on this side you will have grains further moving. Okay. So, this is your parent metal that is moving in this direction. So, this is your parent grain structure, and this zone. So, on this side also some grains are melted. So, you have grains melted partially in these cases. So, this zone is known as the fusion zone, and then on this side you will have the growth taking place. So, as we have understood, you will have the different zones, different growth or columnar growth of the grain taking place in these directions. So, you will have the fusion phase here, and from here the columnar grains will be growing in this direction. So, you will have so as we discussed, you have three zones. You have weld metal zone, you have heat affected zone, and then you have base metal zone. So, these are the 3 different zones which occur. Now, in this case if you have fusion zone, so up to in this side up to certain distance the structure will be changed. There is likelihood that the structure and properties also get changed. So, that is your heat affected zone, and then this is your then you have on this side you will have the base metal zone, and that is unaffected zone. So, unaffected base metal zone, and then towards this side up to in the pool. So, you will have growth from this direction also. So, this side it will be the weld metal zone, which will be here in this case. Now, heat affected zone basically which is here from this side. So, that will have, so there will be up to certain distance this heat affected zone will be defined, and that is because of the heating and cooling effects. So, for that about it we will be discussing further. So, coming to the weld metal zone. So, if you talk about the weld metal zone. So, weld metal zone is basically formed by the solidification of the weld pool. So, you will have the melting in the central part, you will have melting of the original material, as well as you have the melting of the filler metal. So, they are getting melted, and that is why it is known as the weld metal zone. Zone. Now, this is something similar to a cast zone or casting. You can resemble it to a cast metal, because in casting also you are melting the material and then allowing it to solidify. So, in this case also you are basically in this zone you are melting the material. You will have melting of the parent material as well as the additional material, that is the electrode suppose is there. So, that also gets melted, and then your parent material is also on the sides. So, so that way you have these material also, some part is melted, and then your if there is filler material or electrode which is melted. So, they all part they form this pool, and that is the weld metal pool or weld metal zone it is. Now, in this zone basically when the molten metal is present. Now, if you look at the temperature on the sides, this is the parent metal or base metal. Now, there is basically high temperature difference between the temperature in the weld metal pool and in just adjacent to it. So, this is basically normally at the suppose the room temperature. So, there is large undercooling and so you will have the large temperature gradient from this point to this point, and so there will be large undercooling being experienced to the metal which is there inside this weld pool, and because of that large undercooling nucleation will occur, nucleation will start, and then once so nucleation will certainly start at the point where the undercooling will be maximum. So, as you have understood. So, on this point basically you will have the nucleation starting, because at this point the liquid metal which is there in this pool it will be in touch with this base metal. So, you will have the largest undercooling being experienced by the grains which are present here, and from here so nucleation will start, and because of the large undercooling faced you will have very fine grains formed here. But then what will happen that as the heat extraction will go on, so opposite to the direction of heat extraction the grains will grow in this direction. So, you will have the growth of grains in the opposite direction, and so columnar growth will be there, and we have understood how this growth phenomena is can be explained basically, because you know that there are two types of growth. One is your growth in the crystallographic direction, another is the easy growth direction. So, that is your easy growth direction, and then you have the growth which is normal to the boundary. So, because the maximum heat extraction will take place normal to the boundary, because you have the maximum area. So, from there, so accordingly your grains will be growing from there, and your grain growth will show that how grain is growing and coming towards the center. So, this way since, and we have already understood that you have all these partially unmelted grains which are there. So, they will be working as the source of nucleation in such cases, and then they will be so from their nucleation will start, and then it will further grow towards the inner side of the weld metal pool. So, that is basically this mechanism is also known as the epitaxial type of mode, or epitaxial solidification, or epitaxial type of growth. So, that way this weld metal pool is defined. Then the next zone, which is adjacent to that weld metal zone, will be your fusion zone. So, if you talk about this, if we have seen in the figure that you have a zone adjacent to the weld metal zone, you have the fusion zone. Now, you have many terms you will come across, like fusion line many times, and but this is normally a zone in which the fusion taking place. So, it's like we also come across the term like fusion boundary many times. Now, what is happening that fusion zone is the one, on one side of the fusion zone you have the weld metal zone, on the other side you have the heat affected zone. So, now in the case of if you talk about the carbon steel welds, then the liquid plus delta zone. So, for carbon steel welds, the liquid plus delta zone which is there, delta liquid plus delta ferrite zone. So, that zone is basically represented as the fusion zone. So, what will happening normally this fusion zone is quite sharp. So, if you try to refer to the iron carbon diagram, so as you have, this is the delta ferrite, and then you have this becomes the gamma, and this is your delta ferrite, and as you know that this is going like this. So, in the weld metal zone, since the metal is molten, it means practically the temperature is more than the melting temperature of the material. So, it will be higher than that, but then this zone which is there in where there is liquid plus delta. So, this is the zone where there is a liquid plus delta. So, that refers to that temperature where you have this temperature of the order of liquid plus where this temperature is corresponding to. So, in this zone you will have liquid as well as delta, that is your. So, there is partial melting of the grains, some solid particles, and also mostly it is liquid. So, that is your that is basically indicative of that presence of that zone. Now, in this zone, so if you if you talk about other structures also where you see the liquid plus solid phase, so that basically will be the indicative of such fusion zone. Now, this zone fusion zone, so if you try to look at its the figure, if you see the schematic illustration of the microstructure of the fusion boundary zone. So, you will have basically this is completely dark. So, you have here this is completely liquid. So, and then adjacent to this liquid you will have very small grains showing, and then further you will have at distant places you have these again you have the coarse grains appearing. So, this is basically the the liquid plus delta zone, and this is the indicative of a fusion zone in such cases. Now, what we see that here basically that will be demarcating, this will be the demarcation line between basically the so you have on one side you have certainly that so weld metal zone, but then when it ends, because it is very sharp. So, when it ends, which that is why many a times we call it as a fusion boundary. So, then your fusion this heat affected zone starts further. Now, in this case you will have the fine as well as the coarse grains. So, basically it is also represented by that line where your composition will be changing from the parent metal to the composition of the weld deposit. So, basically you will have the composition change from that of parent metal to uniform weld deposit. So, basically you have weld deposit on one side, and on other side you have the parent metal. So, your composition will be changing from this to that. So, that region will be basically the that will be represented, that will be told as the fusion zone in strict sense. Now, after the fusion zone you will have the heat affected zone. So, once you go to cross the fusion zone, then comes the heat affected zone. Now, heat affected zone, as the name indicates, in this case there will be so as we see that you have on one side you have a weld pool where it is completely molten, then you have a fusion zone where it is where on the composition will be changing from the parent metal to the composition of the weld deposit. Now, after that you have the heat affected zone. So, as the name indicates, it is also known as HAZ. Now, in this basically it is that part of the welded joint where the temperature has been raised, and it is raised till the solidus temperature, because after that you have the solid plus liquid region. So, that becomes the fusion part, fusion zone part, and then after that even after the liquidus, so you will have the weld metal zone where the phase is completely liquid. So, that way you have so below that fusion zone you will have the heat affected zone which is formed. Now, in this case what is happening? So, your this is a part of the welded joint which has been heated to temperature up to solidus temperature of parent material. Now, since you are heating the material to its solidus temperature of the parent material, so you also expect a large amount of changes in its properties, in the properties of the material or macrostructure of the material. So, in the heat affected zone, there is a likelihood of change in the macrostructure, change in the properties of the material. Now, many a times you have basically some of the material where the polymorphous transformation does not take place. So, when you have metals and alloys without the polymorphous transformation, so when metals are or alloys are without polymorphous transformation, so in those cases the macrostructure in the HAZ will be not altered. So, because the metal where the polymorphous transformation is taking place, crystal structure basically is changing. In those cases, because you have the, if you talk about iron, so there you have, as the temperature comes down, you have the, initially you have delta farad, then it comes to gamma farad, then gamma austenite, then it comes to delta ferrite. So, you have at different temperatures, you have different crystal structures are there. So, this transformation taking place. So, when the metals or alloys which are without the polymorphous transformation, like say for example copper, nickel or aluminum. So, when you do the welding for these materials, so in those cases your HAZ, the microstructural changes in HAZ is not so much of change. So, microstructural changes in HAZ remain more or less unaltered. But that is not the case for everything is not unaltered. Basically the recrystallization or grain growth still may take place because the temperature is increased. So, you have grain growth or recrystallization may take place. Now, if this is for the materials which does not undergo the polymorphous transformation, for the material which undergo the polymorphous transformation. So, for materials undergoing polymorphous transformation, so suppose you have just like steels where these things are very much prevalent. Now, in those cases you have the macrostructural changes visible in the heat affected zone, and since there is change in the macrostructural appearance, there is change in the microstructure of the specimen in those regions where it is subjected to the temperature change. So, ultimately there will be property variation in those zones. So, basically what happens that when you talk about the this HAZ, so it is that zone where the temperature has been increased, and basically, so certainly upper limit is the solidus temperature, but the lower limit it may go up to a temperature where it can it has done certain changes into the into the structure of the material or macrostructure of the material. So, basically if you talk about typically for the steels, so in those cases you have the HAZ of steel is basically divided into different zones, and these zones are basically, one is the underbeat zones. If you talk about the different zones, so in the HAZ, so you have different zones in HAZ, as one is your underbeat zone. So this is the zone basically where so this is that part of HAZ which is heated beyond the critical temperature of grain growth, and extends up to the fusion boundary zone. So just below the fusion boundary zone, and this is basically the zone where you have this is beyond that critical temperature of the grain growth. Then after the underbeat zone, you have the grain growth zone. So it will be basically towards the, so if you look for the gamma region of the or austenitic iron region, so in the upper half portion, so from there it will extend till the peritectic temperature, that is your grain growth zone, because in that zone the grain growth is taking place. Similarly, you have the grain refined zone. So grain refined zone basically will be that zone which will be towards the lower half in that austenitic zone. So that will be from 950 to 1150 degrees centigrade. In that zone, that is known as the the grain refined zone. Then after that you have other zones, like you have partially transformed zone, and then similarly you have zone of spheroidized carbides. So basically the partially transformed zone will be between the intercritical temperatures. So between A1 to A3 you will have partially transformed zone, and the zone of spheroidized carbides is basically starting from 550 degrees centigrade, it will go till A1. So even at that temperature also when the material is undergoing that thermal treatment, it is being heated, then it is likely to affect the microstructure of the property and correspondingly the properties of the material. So that is the zone of spheroidized carbides. So so this way you will have the different zones, and that we will discuss in our coming lectures, that how these different zones are there. So basically they can be mapped on the iron carbon diagram, and you can have a feel about these different zones on that pertaining to the different temperatures which are achieved. And then depending upon the temperature, maximum temperature up to which they are heated, their properties will be also changed. So these are the different zones in the heat affected zones, because in those cases if you are talking about the grain growth zone, so your grain growth takes place, and growth of the grain will affect the mechanical properties. Similarly, you will have if you come to the on the lower side, you will have the zone where there will be spheroidization of the cementite particle taking place, that is spheroidization process. That is also a process of heat treatment. So there will be some globalization, or there will be globules of cementite which is formed because of these thermal variations. So ultimately you will have its effect will be there on the final properties of the material. So altogether what we have studied in this lecture is that you have, when you do the welding, so apart from the weld pool, you have basically, when we talk about the materials which undergo the polymorphous transformation like iron or steel, in those cases it has strong effect on its mechanical properties. And so many a times when you do the welding, you need to go further for the post treatment many a times, because if you feel that because if since it is subjected to the temperature variation, so it is like a heat treatment process to it, and in these cases you must have the idea that there is a very large rate of cooling many a times. So you may have the development of stresses, then you have coarsening of also the grains that may also take place in certain cases. Then there are other things also which are likely to happen that we have understood. Whichever process is bound to follow during the process of solidification, they are likely here, because that is also in the weld metal zone also it is like the synonymous of a cast specimen, where you are putting the liquid metal and then it is allowed to cool in a metallic mold. So here basically the amount of liquid is even smaller and it is surrounded by the metallic mold kind of thing. So in those cases many a times that will affect the properties or that there will be other associated phenomena like segregation and all that. And on the other side you have the affecting the mechanical properties. So this is all about the heat affected zone in the case of fusion weldments. Thank you very much.